So I have all this data, now what? If you heard that question from farmers, retailers, and so forth, I actually have that in my office. I have all this data, now what? That sort of led my efforts over the last 10 years or so, and that's what we're going to kind of talk about today. I have all this data, now what? How are we going to use it for farm management decision making? I'm going to give a little background on how farmers have used computers over the last, well, since the mid-'80s. Initially, computers were used for record keeping, which is sort of a logical thing to do. It was a good thing to keep records on a computer as a step forward. You know, there's a few images of some guys working at the farm computer, and I like cartoons, and this reminds me of the pet computers we had back in the 80s. But that worked. But then along came precision ag, which changed the way farmers use computers. We had computers on farm equipment. We had computers handheld with GPS. And that caused farmers to have a lot more questions. They were gathering data, asking a question. We have all this data, now what? Researchers were looking at each other like, we don't know. And a lot of time and effort has been put into this by a lot of really smart people. And unfortunately, we haven't really moved very far over the last decade. And I'm going to explain why. When we're trying to analyze data from precision ag, typically what we've done is stare at images like this. How many of you have done that? Brought up images of, how far did that get you? Well, as Rick said, we at Purdue, we put a lot of time and effort into developing techniques to do this, and I had a really good idea. I invited some of the best farmers from across the Midwest to come to Purdue, and here they are. And bless their hearts, they really do want to learn how to do this, and I suspect none of them are doing it right now, even though they've gone through the training with me. And this is where most of them wound up. Because it's frustrating. And it takes days, maybe a few weeks to analyze a given field, to do it the right way, with a human being actively participating in every step. So farmers not farmers to set a computer is analyzing data. And the people who have the capability to offer this type of service, well, how many fields can they do in a given year? A handful? Probably not the thousands of fields that we could potentially have in the marketplace. So let's talk about technology for a second, and I think this will make a lot of sense. Technology in general, and precision ag in particular, can be categorized in two different schools of thought. One side is the information side, the data side, information intensive. Historically in ag, this is field level data used to make decisions. It requires additional abilities, additional skills, more data to make decisions. What's the classic example in ag? Well, integrated pest management. IPM's a good thing. However, it took more skill on the farmer's end to use IPM than before the technology existed. The other side of that coin is embodied knowledge. The technology is built into the input. Maybe a lot of technology there, but it's built into the input. It requires no additional skill, and in the case of the classic example of biotech soybeans, it required less skill to produce biotech soybeans than it did with conventional varieties before. And we have pretty good evidence that farmers liked the convenience of that and adopted that technology readily. Farmers quickly adopted these things. These things, they're more hesitant and are waiting until it's been proven to be effective and easy. So the same question with the precision ag example, information intensive. Well, we're all here talking about data. Yield monitors produce a lot of data. Is it easy to use this data? No, it's not easy. What about taking soil sample data and trying to make variable rate applications? Takes a lot of effort, takes a lot of know-how. Frank was talking about the need for agronomists. Several people have to be involved in this. This all revolves around data. Data, data, data. What about the other side of the precision ag coin? The information, we talk about information intensive. What about embodied knowledge? The classic example in precision ag is automated guidance. What's the adoption curve of automated guidance look like in the last 10 years? Very steep compared to anything else. We have some technologies that are catching on-the-go applications based on sensors within the field, where the decision maker is completely taken out of the process and replaced by algorithms. Those things are being adopted. The difference between these two columns is information intensive is all about data. Embodied knowledge can be considered automated. Automated technologies are adopted a lot quicker. Automated guidance, is it profitable? It doesn't really matter. It's convenient, and therefore people are going to adopt it and use it. My goal in all my research is trying to move the data side of precision ag into the automated realm, removing the human capital from the process. So I speak to a lot of farmer groups. I suspect we're sort of all on the same page, but I wanted to review how farmers are using yield monitors. This is USDA data. This particular slide is for 2002 with soybeans. And these are the options the farmers had to choose from. The question was, if you have a yield monitor, how do you use it? Well, the red lines are with a GPS, and the third highest ranking use of a yield monitor was to conduct field experiments. That was encouraging for me. The same question was asked in 2003 of cotton farms. The highest use of a cotton yield monitor was conducting field experiments. And in 2005, corn was sampled and is identically the same as soybeans. The third highest use of a corn yield monitor was to conduct field experiments. Okay, so we know that there is a need from the farm level for analysis, because how are they analyzing this data? Are they analyzing the data? Well, let's review the steps of on-farm research really quickly. It's like anything else. You have to design the experiment. And we collected data. With yield monitors, it becomes a lot easier. And data use. Manage the data, analyze the data, make decisions, evaluate. Which of these steps do farmers put the most effort? My guess is the implementation stage. Where do they put the least amount of effort? All the others, particularly analysis. And this is a little table, sort of the same steps. This is the old school way, where it says manual, and then the way it's actually going to work in practice, the automated side. The one in particular we're talking about today is this one piece under analyze. Spatial analysis is becoming automated, and that's what Rick had introduced a little earlier. So I asked the question, how do farmers analyze yield monitor data? Any guesses? You know, they kind of stare at it until the data confesses. And I really like the response when working with people. They don't get the results that they wanted, so they start deleting points because, you know, I don't think these were correct over here. And I'm like, well, why did you do the research if you knew the answer? It's very subjective, very misleading, very biased. And the problem with this, one of my pet peeves, have you heard the expression, precision ag is just a bunch of pretty maps? You've heard that? You struggle with this too? I hate that expression, and one of my goals in life is to overcome that obstacle. When we treat mapping or the GIS portion as the ending point, we give validity to that statement. And we got to move past that. Somewhere along the line, we started doing numerical analyses, taking averages by zones or by soils, and that was a step forward, but it's really not getting us anywhere, because if there's a 5 bushel difference between 2 soils or 2 experiments, is that 5 bushels real? How can we tell? Well, we cannot with this method. Well, then eventually we took another leap of faith to a traditional statistical analysis being applied, non-spatial. However, traditional statistical analyses were developed in the 1920s and for small plots, assuming that there's no variability in those fields like Rick was talking about. But in reality, we have variability. And if we ignore that variability, it's going to lead us down the wrong path. So, one of the things I spent my career on is in spatial statistical analysis. When I say this term, I'm not talking about mapping. A lot of folks will refer to spatial analysis as the mapping portion, and that's fine. But I'm talking about the spatial statistical analysis. And as Rick mentioned, it's developed in health sciences, epidemiology, criminology, geography, and so forth. We could get into the math of that. I was telling Rick when we were planning that, Rick, I really don't want to bore them with a bunch of equations. And Rick leans back and says, you don't need equations to bore them. You can do that all by yourself. So we're not going to use any equations. I want to explain why you shouldn't stare at yield maps. Sort of, it's real reasons. And then I'll give you a brief reason why we shouldn't rely upon non-spatial statistics. The good news, there's a good news and bad news about staring at yield maps, or about the human brain and the human eye together. It's excellent at finding patterns, even when a pattern does not exist. You will find a pattern. That's what we do. We're people. Do you see black dots? Would you please count them? What do you see here? If you stare at the crosshair without blinking, raise your hand when you do not see pink. And slowly the hands will, just go across the room. If you look at the room as that happened, you'll realize that the person sitting next to you may be seeing something different than what you're seeing, even though you're looking at exactly the same thing. This is animated, if you're wondering. This is not. This is a still image. What do you see? I just told you the still image. Okay, you see movement. Where do you see the movement? Okay, kind of difficult to assess that. How about this one? Do you see the blue and the green? Okay, the blue is really this color, and the green is really this color. It's the same. Staring at yield maps will be very misleading. I'm going to zoom in on this. That blue and the green is exactly the same color. It's the orange and the hot pink contrasting with it makes you think it's different colors. So, you've seen dots where there were none, you couldn't count them. You saw pink dots disappearing. Did you see the green dot? The green dot wasn't there. That was in your mind and your eye. You've seen movement where there was none. You've seen colors, exactly the same color, but you saw them as different because we're people. We find patterns. Now, I use this example to explain why farmers should not use eyeballing as a technique to analyze yield monitor data. And I'm going to go through a few more explaining why traditional statistics aren't going to work. So with the field experiment, a lot of times we're asking the question, okay, we've got these 4 things going on. Are they the same or different? So here, are they the same color or not? Well, I'll tell you, these are different colors. But what if we threw some noise across this thing? Well, this is white noise. Traditional statistics can help us determine if those colors are still different. But what happens in space, in real world, the noise is correlated. It's not white noise. Something like this. And it's more difficult to negate that spatial variability with traditional statistics. But with the proper spatial statistical analyses, we can determine if those four colors are different. So, give you another example. We have these four experimental designs. So A and B, let's say, are two different cultivars, cultivar A, cultivar B. Upper left-hand corner is split field, side by side, no replications. Upper right-hand corner is replicated once, and then this one's 4, and this one's 8 times. Which one's the easiest one to put into a field? Which one's the most likely to be screwed up somewhere along the way? That's something to consider. So we have a field, and as Rick mentioned, this field has variability. And we could throw these experimental designs across these fields. And this is an experimental design that's largely chosen by farmers because it's easy. And most of the people I work with, the person making the decision is not the person driving the equipment. The person driving the equipment works for $7 an hour about 6 months out of the year. Think about that. Now we have this yield data sitting below it, looks something like this. And we're asking the question, can we get good data from comparing these two treatments versus this? Well, this is better than this, but it's not always going to be very likely to occur. So what will be the value of spatial statistics? These are 5 different representations of variability. This one is a perfect world. It's a random assortment of variability. We can easily handle that through traditional statistics. But as we move to the right and on the second row, the lambda goes from 0 to 0.9. 0.9 is what we expect to find in agricultural fields. It has a strong clustering. Okay, just showing perfect world, sterile environment, classical statistics work. Real world, classical statistics will not work. So this is the accuracy. If you're interested, these are the results for the mean squared error, which is bias and variability. Under the sterile environment, no spatial variability. It doesn't matter. We can have split fields, replicated fields, non-spatial, spatial analysis. It doesn't matter because it's a sterile environment. But under a real world environment, it's much different. The lower the bar, the shorter the bar, the better. So if we have a non-spatial analysis with split field, we're not very likely to make a good decision from that results. With spatial analysis, even with a split field design, it increases the probability of us making the right decision substantially. Not significantly, substantially. Rick's no longer allowed to use the word significant. So what if we have a field looks like this? How many of you have these where you're from? How many of you gotten lost? Well, what if we treated this as an experiment? Okay, we've got some really good corn, and what if we put a couple of strips of a fungicide, a herbicide, tillage treatment, whatever? Well, it'd be a mess to analyze this data, wouldn't it? Because we have all these craziness going on. With spatial statistical analysis, if handled appropriately, we'd be able to tell you if those treatments had a significant impact on yield or not. So I wanted to leave you with this idea of how complex spatial analysis is and how a Rick's system would be beneficial. If we have a wave wagon approach, the math is pretty simple. We have two calculations. We're going to divide total yield by the area, get bushels per acre, and compare the two. Not really complicated. Computational time is kind of inconsequential. Human time, maybe 30 minutes. If we use a non-spatial analysis, a traditional analysis, of course this would be on a computer, we're looking at over 100,000 observations, 100,000 calculations for a 20,000 observation study. It takes about 1 minute on most computers, probably a lot less. The GIS portion is going to take 2 hours, and the analysis for the person is going to be roughly an hour. To do the appropriate spatial statistical analysis, a lot more calculations, probably 5 times as many. Depends on several factors. Takes about 90 minutes on a computer, on a good computer. And GIS is going to be the same as before, 2 hours. The analysis for the person is going to be about 4 hours. And this is 4 hours of locked door, no telephone, so there'd be like 3 weeks of real time. And then with the automated cost of the computer automated spatial analysis, there's a lot more calculations being involved. The computational time is being limited, roughly 20-25 minutes for most things right now. My goal is to get it further down than that. Human time, we're not measuring that because the human's not involved. We've removed the human from the process. The future of precision ag, we've been talking about making data side more automated. I think that's what we're all here to talk about, right? Make it easy to use. The analysis is happening in a cloud somewhere. Someone the other day told me I misused the term cloud. I just walked away. And talking to farmers, and I think David and Frank both mentioned this, farmers tend to be kind of protective of their data sometimes and they don't have the confidence to share that with everybody. And I try to explain that if they keep it to themselves, that data is only valuable to them. And if they pull it together, more benefit to them and everybody else occurs. From my research, I've noted that farmers using spatial analysis are more confident. They make more decisions more quickly. Why? Well, what's the value in improving the chances of being right? That's what spatial analysis does. If we have a 15 bushel difference between two treatments, is that difference real? Well, the only way we can tell that is with spatial statistical analysis. Otherwise, we don't know if it's just an artifact of the data, the measuring devices, and so forth. It takes a spatial statistical analysis for it to happen.